video, we are going to see ADC, pulse width modulation and deep sleep. So first, let me give a short introduction about these topics. First one is ADC, which is analog to digital conversion, which is a process by which analog signals are converted into digital signals. Analog signals is nothing but a continuous voltages and digital signals is nothing but discrete values. So that can be processed by a digital system like a microcontroller. In ESP A26 there are one or more ADC channels that can be used to measure analog signals. The resolution of the ADC in ESP A26 is 10 bits, which means that it can represent analog voltages as the number between 0 and 1023. And coming to pulse width modulation, which is also a technique used to control the power delivered to electrical devices like motors and LEDs. So in ESP 8266, pulse width modulation can be implemented on any GPIO pin. So the duty cycle of the pulse width modulation signal determines the amount of power delivered to the device. The duty cycle can be adjusted by changing the pulse width of the signal, which can be done using the AnalogRight function. And coming to deep sleep. Deep sleep is a low power mode that can be used in ESP 8266 to conserve power. When the device is not actively processing data, in deep sleep mode, the device shuts down most of its components and goes into a sleep state. This mode can be useful in battery power devices where power consumption is the concern. So, to exit deep sleep mode, the device need to be reset or wake up by an external event like push buttons or something. So, let's see one by one in detail. So first one is ESP 8266 ADC. We are going to read analog values with Arduino IDE. So ESP 8266 12E have one ADC pin that is easily accessible. This means that those ESP 8266 boards can read analog signals. When referring to the ESP 8266 ADC pin, you will often hear these terms interchangeably like ADC, T out, pin 6, A0, analog pin 0. So all these terms refers to the same pin in the ESP 8266, which is A0 pin. And coming to its resolution, ADC pin has 10 bit resolution, which means you will get values between 0 and 1023. And ESP 8266 input voltage ranges 0 to 1 volt if you are using bad chip. However, most ESP 8266 development boards comes with an internal voltage divider. So, the input range is 0 to 3.3 volt. So, ADC voltage range in ESP 8266 development board is 0 to 3.3 volt. For example, ESP 8266 12E mode, Node MCU kit or VMOS D1 mini. ADC voltage range in ESP 8266 chip is 0 to 1 volt. For example, ESP07 chip or ESP12E chip. And coming to this analog pin, with the ESP 8266 12E Node MCU kit and the other ESP 8266 development board, it is very easy to access the A0 pin. You simply connect a jumper wire to this pin. If you are using ESP 8266 chip like the ESP 826607, you need to solder a wire to that pin. So this is all about ESP 8266 ADC. So again I am telling you this valuable information. You can convert this masterclass into internship. So let me tell you what are the benefits you will get in this internship, right? So in this internship, you will get 30 days of live recording sessions. You can get access to all the records. You will get 8+ project source code. You can join the VIP community group. You can download all the presentations. you will get internship confirmation letter, and after that you will get internship certificate. So the actual amount of this internship is for 1,999, but there is a discount amount which is available for you, which is only for 799. So this is the registration link. Go for it and make your registration. And the last date to register is 5/6/2024. Make use of it. And these are the ads-on project you will get in this internship, which are smart street light using LDR and IR sensor, monitoring soil moisturization using sensor, gas leakage detection using Arduino IoT cloud, and IoT based heartbeat monitoring system, and BME 280 sensor readings to the real-time database, web-based remote serial monitor, sending email using SMTP, and telegram request to the sensor readings. And also there is a 3-in-1 bundle course is available for you. In the lineup you will get IoT, embedded system and Arduino. And the registration actual fees is 1,999, but there is a discount amount which is available for you, which is only for 999. So this is the registration link. Go and grab it, and the last day to register is 5/6/2024. So make use of it. And what are the benefits you will get in this bundle course? You will get 90 days of live session, 1 year validity, 20 plus project source code, and you can get access to the VIP community group, and you can download all the presentations. You will get internship confirmation letter and internship certification. So now let's get back to the code. So here first we are going to initialize analog pin. For that I am going to use constant integer. I am going to take like analog pin, which is equal to A0. And next, this allows the programmer to tell the compiler that a particular variable should not be modified after the initial assignment in its declaration. Then we are going to create a variable called pot pin, which is nothing but potentiometer pin. So integer pot pin. Here I am going to give 0. So the potentiometer value will be stored on the pot pin variable. So inside void setup, I am going to define baud rate using serial dot begin. Inside I am going to pass 9600 as baud rate. Then inside loop function, we have to read the analog pin value and we have to store it in a variable. We have already created a variable called pot pin, right? So in pot pin, I am going to read my analog pin. Inside I have to pass analog pin. So we read the analog value by using AnalogRight function and passing that analog pin as an argument. So the value is saved on the set pot pin variable. So now let's print the value on the serial monitor. For that I am going to use serial dot print. Inside I am going to give a message like pot value. Again, now we have to print that value. So here I am going to print pot pin value. Then we have to give delay for 1 second, which is 1000 millisecond. So now let's move to the hardware part. So here this is ground pin, the center one is analog pin, and the third one is VCC pin. We have to connect it accordingly. So the first pin, orange wire, has to connected with ground, and the center pin has to be connected with A0, and the third pin is VCC. We have to connect it with 3 volt. This is our connection. So let me upload the code into the ESP A26. Before that, make sure you have selected the correct board and port. Yeah. It's uploading. Let's wait for a few seconds to get fully uploaded. Yeah, it's uploaded. If you open your serial monitor, here you will find your output. It's connecting to the port. Yeah, here. If I adjust the knob, according to the knob, the value will change. Here you can see like 177, the value is decreasing. So if I adjust the knob, the value will gradually increase. So the maximum value is 1024, right? So this is our output. So now let's move to the next topic. So now let's interface one analog sensor with ESP A26. Here we are going to use LM35 temperature sensor. So this is our LM35 temperature sensor that outputs an analog voltage which is proportional to the temperature in Celsius. It is a popular choice for temperature sensing applications due to its accuracy, low cost and ease of use. So if you see the pin out, here the LM35 sensor has 3 pins, VCC, ground and output pin. The VCC pin is connected to the positive supply voltage and the ground pin has to be connected with the ground, and the output pin provides an analog voltage output which is proportional to the temperature. So the LM35 operates over a temperature range of minus 55 degrees Celsius to plus 150 degree Celsius. So the output voltage is linearly proportional to the temperature with a sensitivity of 10 millivolt per Celsius. So the output analog voltage can be converted to a digital form using ADC so that a microcontroller can process it. So now let's write a code for LM35 sensor. Okay. So here let me erase it all. First I am going to initialize a float variable called Vref, which is voltage reference with the value of 3.3. This variable represents the voltage reference of ESP A26 ADC. Again I am going to initialize a float variable called resolution by dividing Vref. Here I am going to divide Vref by 1023. This calculation determines the resolution of the ADC or the smallest voltage increment that can be detected by the ADC. So now we have to create void setup function. Inside I am going to begin baud rate using 9600. So now void loop. So inside void loop, we have to read the sensor pin and we have to store it in a variable. For that I am going to use data type is float. Here I am going to create a temperature. Here I am going to read that analog pin. Here we read the analog voltage from pin A0 using AnalogRight function and we are going to store it in a float variable called temperature. Now to convert ADC reading to a voltage value, we need to do one calculation, which is, here I am again going to store that value in temperature. What is the calculation is, we are going to multiply this temperature with resolution. So it multiplies the temperature value by the resolution value to convert the ADC reading to a voltage value. So now we have to make another calculation for that converting temperature value in degree Celsius. For that Again temperature. Here we are going to multiply temperature with 100. Temperature, I am going to multiply it with 100. So now we have to print that in the serial monitor. So serial dot print. Here I am going to temperature serial dot println. Here I am going to give like degree Celsius. Now we have to give a delay for like 1000 millisecond, which is 1 second. Yeah, that's it. So if we move to the hardware part, here this is our LM35 sensor. I'm going to place it here. You have to place this flat side towards you. I'm going to place this like this. So the first pin from left is VCC, which is we have to connect this with 3 volt, and the center pin is output pin. We have to connect it with A0, and last pin is ground. We have to connect it with ground. This is our connection. So let's upload the code now. Yeah, it's uploading. Let's wait for a few seconds. Yeah, it's uploaded. If you want to make changes, you have to make some heat near the LM35, or you can just rub your hand and hold your LM35 sensor for a few minutes. You can get different values like this. Yeah, 8 something. So this is our output. Now let's move to the next topic. Next is pulse width modulation. So let's see. So now we are going to see how to generate pulse width modulation signals with ESP A26 node MCU using Arduino IDE. As an example, we will dim the LED brightness by changing the duty cycle over time. So the ESP A26 GPIOs can be set either to output 0 volt or 3.3 volt, right? But they can't output any voltages in between. However, you can output fake mid-level voltages using pulse width modulation. If you alternate an LED's voltage between high and low very fast, your eyes can't keep up with the speed at which the LED switches on and off. You will simply see some gradations in brightness, right? That's basically how pulse width modulation works. By producing an output that changes between high and low at a very high frequency. And there are two important parameters associated with pulse width modulation signal. First one is duty cycle of pulse width modulation. As we know, a pulse width modulation signal stays on for a given time and stays off for a certain time. The percentage of time for which this signal remains on is known as the duty cycle. The on time is known as duty cycle. If the signal is always on, then the signal must have a 100% duty cycle. If it is off in the cell, it will have 0% duty cycle. So the formula to calculate the duty cycle is duty cycle, which is equal to turn on time, which is divided by turn on time plus turn off time. The average value of the voltage depends on the duty cycle. As a result, the average value can be varied by controlling the width of the on of a pulse. And the next one is frequency of pulse width modulation. So the frequency of pulse width modulation determines how fast a pulse width modulation completes a period. A period is nothing but on time plus off time, which is called a period. So the frequency of pulse width modulation can be calculated as 1 divided by time period. How we calculate time period? On time plus off time. And then here comes AnalogRight function. To generate a pulse width modulation signal on the ESP A26 pins with Arduino IDE, we have to use AnalogRight. Inside you have to pass pin and you have to pass value. The pin, we can use pins from 0 to 16, and value is an integer between 0 and 255. It should be in range from 0 to pulse width modulation range, which is nothing but 255 by default. When value is 0, pulse width modulation is disabled on that pin. When a value is 255, this corresponds to 100% duty cycle. You can change the pulse width modulation range by calling this function. And then AnalogRight range, inside you have to pass new range. And by default, ESP A26 pulse width modulation frequency is 1 kHz. You can change pulse width modulation frequency with this function. And then AnalogRight frequency, inside you have to pass new frequency. The valid values are from like 100 Hz to 40,000 Hz. So now let's write the code for this. Let me open Arduino IDE. Let me erase it. So first I am going to start this by defining the LED pin. So constant integer LED pin, I am going to give like D1. Now inside void setup, I am going to do nothing because there is nothing to pass inside void setup. We have to write code inside void loop only. So inside void loop, we have to create a for loop. For what? To vary the duty cycle between 0 to 255 to increase and 255 to 0 to decrease the LED brightness. For that, first I am going to create one for loop. Inside I am going to give like integer duty cycle. Here I am going to give 0 and then duty cycle. Here I am going to give less than 255 and then duty cycle I am going to make an increment. So inside I am going to give analog right. Inside we have to pass pin and value, right? So pin is LED pin and value is duty cycle. We have already mentioned here. So this function uses pulse width modulation to vary the brightness of the LED by rapidly turning it on and off at different duty cycles. So now I am going to add a delay of 10 millisecond, just 10. Using the delay function to slow down the change in brightness and make it visible to our eye. And then another for condition, for loop, for to decrease the brightness. So same, int duty cycle, here I am going to give 255 and then duty cycle, here I am going to give greater than 0. Here I am going to make decrement. So same, again using AnalogRight function, we have to pass LED pin, comma, duty cycle. So again delay of 10 millisecond. So that's it. Now let's move to the hardware part. We just need LED, resistor and 2 jumper wires. Here I place LED and resistor here. The negative leg, which means the short leg has to be connected with ground, and we have taken D1 pin as LED pin, right? So the positive side of the LED has to be connected with D1 here. Now let's upload the code into the ESP A26 board. Yeah, it's uploading. Let's wait for a few seconds. See, here you will see the output. Your LED brightness is gradually increases and decreases. So this is our output. So next topic is deep sleep. So now we are going to learn about how to use deep sleep with the ESP A26 using Arduino IDE. Here we will cover deep sleep with timer wake up and deep sleep with external wake up using the reset pin. If you have made a project with an ESP A266 board, that is battery powered, or if you just connected your ESP A266 node on CU board to a power bank, so after running it for a while, you realize that battery doesn't last long, especially if you are using Wi-Fi. If you put your ESP A266 in deep sleep mode, it reduces power consumption and your batteries will last longer, right? So having the ESP A266 in deep sleep mode means cutting with the activities that consume more power while operating like Wi-Fi, but leave just enough activity to wake up the processor when something interesting happens. So now let's see the type of sleeps. Actually, there are 3 different types of sleep mode. One is modern sleep, light sleep and deep sleep. If you are taking modern sleep, in this mode the Wi-Fi modem is turned off while the CPU and system clock and RTZ remain turned on. So this mode allows the microcontroller to wake up quickly and connect to the Wi-Fi network when needed. If you are taking light sleep, in this mode both the Wi-Fi modem and the system clock turn off while CPU and other components such as RTZ remain on. This mode consumes less power than mode sleep but takes a bit longer to wake up. And then comes deep sleep. In this mode almost all system components including CPU and system clock are turned off except the RTC. This mode consumes the least power and has the longest wake up time. So this table also shows the power consumption of the Wi-Fi module in different states. When the Wi-Fi is turned off, it consumes no power. When it is turned on, it consumes a significant amount of power, which depends on the level of activity like represented by DTIM values in the table here. So the table provides an estimation of average current consumption in milliamperes for different scenarios. Assuming the microcontroller is operating at 3.3 volt power supply. So the lower substrate current in deep sleep mode signifies minimal power consumption, which makes this mode suitable for battery power devices. But power conversion is a crucial factor. So note that the power consumption on the table refers to the ESP A266 as a standalone chip. When we are using a development board, they have passive components that use more current. See here, they all have different purposes and they should be used in different applications. But here we will cover deep sleep mode. So everything is always off except the real-time clock, which is how the ESP A266 keeps track of time. So this is the most power efficient option, and the ESP chip only draws approximately 20 microampere. However, if you use a full feature development board with built-in programmer like LEDs and so on, you won't be able to achieve such a low power state. And then coming to wake up sources. So after putting the ESP A26 in deep sleep mode, how can we wake it up? There are different ways to wake it up. One is timer wake up, another one is external wake up. So here the ESP A26 wakes itself up after a predefined period of time. And in external wake up, the ESP A26 wakes up when you press the reset button. So the ESP A26 restarts. So here the first one, to use timer wake up with ESP A26, we need to connect the reset pin to the GPIO 16th pin. This is labeled as D0 here. But we have to connect the reset pin to GPIO 16th pin only after uploading the code. After uploading the code, you have to connect reset pin with GPIO 16th pin. So the reset pin of the ESP A266 is always high while the ESP A266 is running. However, when the reset pin receives a low signal, it restarts the microcontroller. If you set a deep sleep timer with the ESP A266, once the timer ends, GPIO 16 sends a low signal. That means that GPIO 16, when connected to the reset pin, can wake up the ESP A266 after a set period of time. So now we will move to the coding part. So let me open Arduino IDE. Let me erase it. So first, void setup. Inside I am going to initialize baud rate. Serial.begin. I am going to pass 9600. And then now I am going to use another function called serial.set timeout. This line set the timeout for the serial communication to 2000 milliseconds. For that, inside I have to pass 2000. So this means that if no data is received over the serial port for 2 seconds, the serial communication will be stopped. So now let's create a while loop. For that I am going to create while inside serial. Let's leave it blank. So this line, this statement waits in a loop until a serial connection is established. This is useful if you want to wait until you see the output of the board over the serial monitor before proceeding. So now what we have to do is that now we can print the message. So using serial.print, I am going to print a message like I am awake, but I am going into deep sleep mode for 30 seconds. So this line prints the message to the serial monitor, so you can see when the board is about to enter deep sleep mode. So now let's put the board into deep sleep mode for 30 seconds. So for that I have to use ESP.deep sleep function. Inside I am going to give 30E6, which is nothing but This is a parameter given to the function is the number of microseconds the board should sleep for. So 30E6 is scientific notation for 30 lakhs microsecond, which is equal to 30 seconds. So now we have to set void loop. So I am going to leave it blank because in this case we don't need to do anything in the loop when the board is sleeping. So now I am going to upload the code. Just let us upload the code. Yeah, it's uploading. Let's wait for a few seconds to fully get uploaded. Yeah. So now I have uploaded the code. Now what we have to do is that we have to connect reset pin with D1. Now our ESP A26 in deep sleep mode. After woke up, it's print the message like I am awake, but I am going into deep sleep mode for 30 seconds. So let's wait for 30 seconds. It will print here. If I press reset button, it will print like I am awake, but I am going into deep sleep mode for 30 seconds. So again, if I press, it will again print the message like this. You will get message after 30 seconds. So this is our output. So you can also wake up the ESP A26 with an external wake up, like the press of a button or a read switch. You just need to put the ESP A26 in deep sleep mode for an indefinite period of time and then set the reset pin to low to wake it up. So ADC, pulse width modulation and deep sleep are most important features of ESP A26 microcontroller that allow it to interface with analog signals, control power delivered to devices and conserve power when not in use. So understanding these features is essential for designing efficient and effective ESP A26 based projects. Yeah. So again I am telling you this valuable information. You can convert this masterclass into internship. So let me tell you what are the benefits you will get in this internship, right? So in this internship you will get 30 days of live recording sessions. You can get access to all the records. You will get 8+ project source code. You can join the VIP community group. You can download all the presentations. You will get internship confirmation letter and after that you will get internship certificate. So the actual amount of this internship is for 1,999, but there is a discount amount which is available for you, which is only for 799. So this is the registration link. Go for it and make your registration. And the last date to register is 5/6/2024. Make use of it. And these are the ads-on project you will get in this internship, which are smart street light using LDR and IR sensor, monitoring soil moisturization using sensor, gas leakage detection using Arduino IoT cloud, and IoT based heartbeat monitoring system, and BME 280 sensor readings to the real-time database, web-based remote serial monitor, sending email using SMTP, and telegram request to the sensor readings. And also there is a 3-in-1 bundle course is available for you. In the lineup you will get IoT, embedded system and Arduino. And the registration actual fees is 1,999, but there is a discount amount which is available for you, which is only for 999. So this is the registration link. Go and grab it, and the last day to register is 5/6/2024. So make use of it. And what are the benefits you will get in this bundle course? You will get 90 days of live session, 1 year validity, 20+ project source code, and you can get access to the VIP community group, and you can download all the presentations. You will get internship confirmation letter and internship certification.